Okay, I just want to start with an announcement about my office hours. I'm going to switch my office hours from Monday afternoon to Monday and Wednesday morning. And I haven't, so today I will be present. I will be there from 2 to 3. So not quite last minute. And then from next week onwards, I won't be there in my office on Monday afternoons. So I will update the schedule and I'll post it on the website, and then also send an announcement or an email so that everyone knows about this. Okay, let's switch to class notebook. All right. All right, solid state BJTs. And I'll recap the physical structure one more time. So a regular PN junction diode is made from a P-type and an N-type material. When we connect two PN junctions together, back to back, we get what is known as a bipolar junction transistor, BJT. This is a side view or a cross-sectional view. Typically, we make these in the X and Y direction. So looking at it from the top, it looks something like this. We have, actually should, let's use a color. And so this is the outer perimeter. I'm going to have in there. Then a small section of blue. Okay. So the image on the left shows us a cross section, right? So it's looking at it from the side. But typically, these are created in the XY direction, looking from the top. Okay, we are working at the micro scale. And at the micro and nano scale, we cannot directly access and assemble our devices. So the way we work is known as with a process known as surface micromachining. We have our silicon wafers, flat. And looking at it from the top, this is, of course, from a, let's see. So this would be a silicon wafer. And it would be broken up into hundreds of devices. Okay, you don't have to draw these. This is just for explanation purposes. And so each one of these devices can contain hundreds of millions of transistors. Okay, each chip that you see here can have hundreds of millions of transistors. And I'm just showing you cross section of like one transistor. So the way it works is you have a silicon wafer, you create an opening in that silicon wafer, you implant your impurities on there, in there, and you create a N-type structure. Then you create a small opening inside that N-type structure and you implant P in there. So now you get like a PNP transistor. Or if you have a N transistor, let's say you want to create an NPN transistor, you would have an N-type N-type material or N-type silicon wafer. You create an opening in the N-type material, implant it with P-type dopants. Inside that P-type dopant, you again create a smaller opening and you implant an N-type material. Now you have an NPN transistor. So looking at it from the top, it simply looks like 3 rectangles, which is what this is. And looking at it from the side is the actual device operation. I mean, we can explain the actual device operation from there. Does that make sense? Do both the views make sense? Okay. Most of you are mechanical engineers, right? MEs. So how many of you have been to the clean room? How many of you know that there's a clean room here? Okay, so it's in building, a little bit of tangent, building 3, not building 3, engineering 3 building 41, I believe. There is a semiconductor fabrication facility that is known as the clean room, where you can actually go, students can go in there. We work with silicon wafers and students will learn the skills where they end up building these devices. Now, the reason I said MEs, but it's not restricted to just MEs. People from all backgrounds, chemical engineers, biomedical engineers, mechanical engineers, electrical engineers, physics, chemistry, all of them come together because all of these skills are needed in semiconductor fabrication. Okay. There is a specialized field known as microelectromechanical systems, which is what I specialized in. So it's microelectromechanical systems. Okay. Acronym is MEMS, MEMS. That was my specialization in graduate studies, microfabrication and MEMS devices. Okay. And so that's where you create mechanical structures which are the size of microchips. It uses exactly the same skills. So that's an avenue for you to go work in the industry if that's something that interests you. There's a class that is offered there every winter quarter, BMET 435 or EE 473, where students can actually go into the clean room and build electronic devices, semiconductor devices. Okay. So that's something you might want to check out in the course catalog. Anyway, coming back to our class. This is a BJT. It's a 3-layer device. Outer layer is the collector, is the biggest physical size. Then you have the base in the middle, and then emitter, which is encapsulated inside all of them. So here, this would become the collector. This would be the base. And this inside, the smallest structure is the emitter. But what makes this structure unique is the doping concentrations. The base is the thinnest and it's the most lightly doped, meaning there are not enough charge carriers to conduct current. Okay, so the base is physically the thinnest or the smallest and is also the least electrically active in the sense of doping. It has the least amount of doping, whereas the emitter has the highest amount of doping out of all 3. Okay, so the emitter is the most heavily doped, meaning it has an excess of free charge carriers. Excess of free charge carriers. Thus, we obtain a device that is not like a true diode. So here, this junction is forward bias, and this junction right here is reverse bias. So the physical structure is similar to that of 2 back-to-back PN junction diodes, whether it's PNP or whether it's NPN. Okay, but the operation is not like a diode. Well, it's actually half and half. Okay? It's not like a true diode. So we have the base emitter junction, and we apply a positive bias to the base and a negative to the emitter. In an NPN transistor, that means we are forward biasing the base emitter junction. And if we forward bias a base emitter junction, it behaves like a diode, like a normal regular diode. However, the collector base junction is not forward bias, it is reverse bias. We're applying positive voltage to the N side and negative to the emitter. And so the base collector base junction is reverse bias. It is held at a higher potential with respect to the base. The operating modes, there are 4 different operating modes. One of those 4 is kind of like a forbidden, meaning it's essentially useless for operation. We don't bias our transistors in that mode at all. But the operating modes depend on biasing. And we'll talk about biasing later on, but the biasing basically is the DC input that we apply to set up the operation of our transistor. Okay. Biasing simply means the DC input that we apply, the DC voltages and currents that we apply to our transistor to set up the mode of operation. Let's look closely at how it actually works. Okay, we have 3 terminals, collector, base, and emitter. We use the standard reference configuration and voltage polarity and the current direction. So let's, okay. Remember, 2 subscript notation, meaning voltage measured at the first subscript with a reference at the second one. VXY means you're taking your meter and connecting the positive terminal to X and the negative terminal to Y. And thus we have 3 voltages here. We have VCE, we have VBE, and we have VBC. To pay close attention to what quantity is being measured or asked for, depending on that, you would have either a positive or a negative answer. And then, of course, we have current direction, IB, IC, and IE. In this case, it's an NPN transistor. So the base and collector current are going into the transistor, and the emitter current is coming out. Okay, IC and IB are going in, IE is coming out. Whatever we discuss here for the NPN transistor, the exact same analysis applies to a PNP transistor, except all the polarities are flipped and the current directions are also flipped. Okay, so in an NPN transistor, IE is coming out. In a PNP transistor, it is going in. Hence the symbol. This arrow notes it's an NPN transistor. It's coming out. The arrow notes that it's an emitter. If the arrow is pointing out, it's an NPN. If the arrow is pointing in, it's a PNP. Okay. And then at the same time, IC and IB are also the opposite. For an NPN transistor, IC and IB are coming in. For a PNP transistor, they are going out. I'll come back to these equations after the next slide. Let's go to the next slide first. All right. So the basic operation of a device, the BJT, is that IB and IC combine to give us IE. Okay. IB and IC combined to give us IE. Hence the equation on the previous slide, which is IE is the sum of IC and IB. Emitter is the most heavily doped region. Hence, IE, the emitter current, is also the largest. Okay, IE is the largest. IE is always the sum of IC plus IB. Also, IB is far smaller. This is not to scale. Okay, IB is typically very small. So if I was drawing a true diagram to scale, it would be 1,000 order difference in magnitude. So IB is very small compared to IC and IE. Typically in microamps. And hence, IC is very close to IE. Actually, and then VCE, of course, is the sum of VCB plus VBE. If we measure this and we simply apply KVL, we can obtain VCE is VCB plus VBE. Okay. Let's go here to this diagram. Explains the basic operation in far more detail. So we have an NPN transistor where we are actually forward biasing. This is N, this is P, and this is N. Okay, so you're forward biasing the base emitter junction. Because you're forward biasing the base emitter junction, behaves like a true PN junction diode, and a lot of the electrons from the N type material, meaning the emitter, cross over into the base region. Okay. At the same time, holes in the P region, meaning in the base, will go over into the emitter. But because the base is very lightly doped, the number of holes crossing over is far smaller than the number of electrons that are crossing over into the base. Okay. Now, some of these electrons that come from the emitter will recombine with the holes that are present in the base, but a majority of them are still free to move around. They have, at this point, they are like, they've moved into a room, they have no purpose. What should we do? We don't know what to do. Okay, that's where the reverse bias comes into the picture. So again, a huge number of electrons is going to cross over into the base. A small portion of those electrons will recombine, and thus we obtain the base current, IB, but a majority of electrons are free because they have nothing else to do. At this point, if we reverse bias the collector junction and we apply a positive polarity at the collector, then the electrons have acquired sufficient energy to cross over from the base junction and now go into the collector. Again, electrons are negatively charged. If we apply a positive voltage, we are setting an electric field that would attract those electrons that are present in the base. Obviously, all of this happens not quite in an instant, but very quickly. Right? And we are applying both biasing voltages at the same time. So you flip a switch, you apply forward bias to the base emitter junction, and you apply reverse bias to the collector base junction. The electrons go from the emitter to the base, and they're attracted through the base all the way to the collector. And thus, we have a resulting IC. Oh, electrons are flowing this way, meaning current IC is flowing this way. Okay. Let's take a pause. What do you think over that? Let me know if you have any questions. Yes. Voltage, or is the voltage always applied to base? In what sense? Which voltage? Okay, so as I think this DC, and the answer to the question, is voltage only applied to one specific terminal? The answer to that is, well, there's two parts. We have DC and we have AC. Okay. So in DC, in diode circuits, we saw we can apply a DC voltage to a diode and then apply AC signals on top of it, right? There we saw the application where you can clamp it either positive or negative. In a transistor, BJT, MOSFET, or FETs, you apply a DC signal to all three terminals. So now the DC voltage that is applied to these three terminals will fix the operation of that device. And then we apply an AC signal on top of it. By far, the most common configuration is we would apply input to the base. So the answer to your question is yes, but it's not necessarily true at all times. The signal could be applied to the collector, could even be applied to the emitter if you wanted to, but then those modes of operation are not what we would use. By far, the most common one is where we would apply the AC input to the base. So DC input goes through all three terminals because that is required to fix the operation of the device. That is what we call as DC bias. We are biasing the device to operate only in a constrained manner. We don't want it operating outside of those constraints. And then we apply an AC signal on top of it. More often than not, we apply that to the base. And then we apply the small signal to the base, and then the transistor would combine is kind of like, I use the term loosely, combines the DC as well as the AC together to give us an amplified out. Okay. But does this basic operation make sense? Right. Forward bias, the emitter and base junction, large number of carriers are injected into the base. Because the base is very thin physically and very lightly doped, a lot of these charge carriers are free to conduct. And because they have nothing else to occupy their time in the base, they're able to go into the collector and complete the circuit. And thus we have a large collector current. And the reason why the collector current is approximately equal to the emitter current is because, again, the base is very lightly doped. Okay, because the base is very lightly doped, only a small fraction of the emitter current goes into the base. The rest of it goes into the collector. So the collector current and the base current combine to give us the emitter current. But because the base current is very, very small, the collector current is almost or very close in value to the emitter current. So the ratio of the collector current, let's go here. So the ratio of the collector current to the emitter current is alpha, and it's typically 0.99 something, because the base current is very small. And then we have beta, which is by far the most important parameter for a BJT. It's known as the current gain. And this is typically in the hundreds. Okay, alpha and beta are the two most important parameters to describe a BJT. So how does it actually work is something that we will look at later on in this chapter. But I'll just give you a brief example. So you have a small voltage applied to the base. So what a BJT does is it takes the AC signal and it takes the large DC signal and it gives us an amplified output. Okay. We take a small AC signal, typically, sometimes it's even in the millivolts, like 10 millivolt, 100 millivolt signal. And we take DC supply, 10 volts, 15 volts, 20 volts. Combine those two together, we can say that the DC voltage is now given the shape of the AC signal, and then we get an amplified output. And that is one of the most important applications for a BJT. Okay. Depending on, so this would be as an amplifier, but depending on the mode of operation, we can use the BJT as an amplifier or as a switch. Said we have 4 total modes of operation, right? One is reverse active, which we never ever use, where both junctions are reverse bias. So that is never ever used. That's the 4th one. Then there is the forward active, which is the mode that I just spoke about, where we use it as an amplifier. And then there are 2 other regions of operation, cutoff and saturation. If we use it in cutoff, then the transistor is set to be off. If we use it in saturation, we say the transistor is on. And so those 2 modes combined means that we can use the BJT as a switch. We can use it for digital applications. So this would be digital applications, and this would be analog. So let's stop right here, and then we'll pick up here again on Wednesday.